Hi everyone. So welcome to lecture number 5 of Data Science and AI GATE course. So we were discussing counting and we already have discussed permutations and combination. But whatever formulas we have discussed so far are permutation and combination without repetition. So when we pick an object, we assume that that object is gone. We cannot pick it again. For example, if you see the player example, the cricket match example, I told you the number of ways in which we can select a team of 11 players out of 15, right? So we were assuming that one player can be picked only once. So all the things which we have seen so far were permutation and combination without repetition. We were not repeating the objects. But now we are going into an interesting domain. We will be seeing combinations and permutations in which there is an infinite supply of objects, you can assume, or like some supply of objects will be given and we can actually repeat objects. We have seen a few such examples. For example, when we saw the number of permutations of A, B, C. So there were two A's and there were one B and one C, right? So there were repetitions somehow. But now we are going to see generic formulas for those, like if we have n number of supplies for certain objects and we can pick them. So first thing which we're going to discuss is combination with repetition. Remember again the difference between combination and permutation. Permutation is arrangement. We need to select and arrange the objects, and combination is just selection. In how many ways can we select objects? So yeah, assume that we have a set A with n elements. Any selection of R objects from A, so again we are selecting R objects from A, where each object can be selected more than once. So this is our set A. It contains n objects and we have to pick R items out of it. We know that if repetition was not allowed, the number of ways to select R objects out of n objects was NCR, right? But now repetition is allowed. We can actually select two, let's say twice. Okay, so repetition is allowed. And so this is called combination of n objects taken R at a time with repetition. Okay, so generally speaking, when questions on this will come, they will explicitly mention in the question that you can assume that repetition is allowed. Okay, so for example, like consider this example: number of ways of selecting 3 letters from A, B, C, D. We have to select 3 letters from A, B, C, D with repetition allowed. So here we can actually select A 3 times. So if repetition was not allowed, what were the number of ways? If repetition was not allowed, we know that the number of ways was 4C3, which is 4. How did I do it so fast? 4C3 is equal to 4C1 and 4C1 is equal to 4. So there were 4 ways. What were they? A, B, C, A, B, D, A, C, D and B, C, D. These were 4 ways. But now repetition is allowed. So we can select any number of object any number of times. So we can select A 3 times. We can select 2 A's and 1 B. We can select 2 A's and 1 C. We can select 2 A's and 1 D. And so on. So these are all the ways. So we have B selected 3 times. We have C selected 3 times and D selected 3 times. And but again, like don't make a mistake. We don't have to arrange them. It is just a selection still. So A, and A will be same selection. This is same selection. We are actually selecting 2 A's and 1 B. So these two are same. We don't have to work on. This is a selection, but repetition is allowed. So this is written in the note as well. Two combinations of repetition are considered identical if they have the same elements repeated the same number of times regardless of their order. Okay, so if you have the same number of elements repeated same number of times, this selection will be considered identical. So these two will be considered identical. Cool. Moving forward. So again, like this is an example. So let us say that there are 2 flavors of juices available in a juice shop. Okay, banana and chocolate. And 3 friends go to the juice shop. In how many variations of orders are possible? So here, like it is a slightly ambiguous question. So one thing is like if you consider these 3 people to be different. Let's say 3 people go to the juice shop. Let's call them A, B, and C. Okay. If we consider these 3 people different, then like the number of like how many options? Like A can order banana or chocolate. The B can order banana or chocolate. C can order banana or chocolate. So there are 8 possible options, right? That way. But this is not what they are asking. They are asking how many variations of orders are possible. So it means that they are asking from the perspective of shopkeeper. How many orders does the shopkeeper has to like make to fulfill all the requests of the three consumers. For example, like these are the possible choices. The orders which are possible are like one order can be 3 chocolate juices, right? All the 3 people wanted a chocolate juice. One possible order can be 1 banana and 2 chocolate. Okay, one possible order is 2 banana and 1 chocolate, and one possible order is 3 banana juices, right? So these are the only 4 choices possible. So here, like again, here ordering was important. So this was permutation with selection. Here we were selecting and then ordering as well. But here ordering is not important. So from the shopkeeper's perspective, what he has to do? The shopkeeper has to make juices, like so the order might be 3 banana, 3 chocolate, 2 chocolate, 1 banana. That's how you ask when you go to a juice shop, right? So 3 friends go and I ask like we want 2 banana and 1 chocolate juice, right? It doesn't matter which one is getting what, because the banana juice is same actually, right? So these are the 4 possible choices. But how do we calculate them? Here the problem was easy. Here it was given. Here it was given that there were only 2 possible juice options and there were only 3 friends. But let's say now, still like there are 3 flavors of juices, but now 10 friends go to the juice shop. Now the problem becomes tougher, right? So let's say again there are 3 flavors. Let's say the flavors are F1, F2 and F3. There are 3 possible flavors of juice and now 10 friends go. So now we have to think about it. Okay, now the problem becomes difficult, and now we are seeing the motivation behind combination with repetition. So what is the problem here? Think about it. 10 friends are going, 3 possible flavors are there. What are the possible options that we have? We can order all 10 F1 flavored juices, right? This is one possible choice. All 10 F2 is also possible. All 10 F3 is also possible. There are many possibilities. So like consider this. We can have 5 F1 flavors. We can have 3 F2 and 2 F3. This is one such possibility, right? So there can be many such possibilities. So whenever a question from combination with repetitions come, there is a standard way to solve it. Just try to create a mathematical equation which symbolizes the question. So what is the mathematical equation? Think about it. So let's say you take x1 number of F1 flavored juices. I am taking x1 number of F1 flavored juices, and I am taking x2 number of F2 flavored juices, and I am taking x3 number of F3 flavored juices. Okay, see, juice shop, you always assume when you go and order, you assume that they have an infinite supply of juice, right? I can take 100, if they don't have, they will actually tell you. But in some sense, you are assuming that they have an infinite supply of juices. So you have like many F1 flavored juice possible. You have many F2 flavored. You have many F3 flavored juices. Okay, you can take 10 glasses from here, 0 from here and 0 from here. You can take 5 glasses from here, 3 from here and 2 from here. That will be one combination. So you are actually picking x1 from F1, x2 from F2 and x3 from F3. The condition is what? That total number of juices you need should be equal to 10, because there are 10 friends going to the shop. So always when a question from combination with repetition comes, try to map it to a mathematical equation which solves the same problem. So here we have to find the number of ways, the number of solutions to the equation x1 plus x2 plus x3 is equal to 10. Where, what is the range of x1, x2 and x3? What is the domain actually? Sorry. So x1 can lie between 0 and 10, right? There is no condition mentioned. So they are asking for all possible variations. So basically x1 can be anything between 0 and 10. See, why am I adding 10? Because x1 cannot be greater than 10. But like you cannot have 11 F1 flavored juices, right? So yeah, you can even skip this condition. The only condition is x1 has to be greater than or equal to 0, right? It can be 0. Similarly, x2 should also be greater than or equal to like 0 and less than or equal to 10, and x3 should also lie between 0 and 10. So this now becomes a system of linear equations. We have 4 equations. and we have to find how many such possible values of x1, x2, x3, the triplet x1, x2, x3 exist which solve this equation. So one such solution is 10, 0, 0. 10 plus 0 plus 0 is 10. It satisfies all the equations. One such solution is 5, 2, 3. And so on. There are many such solutions. And we have to find how many solutions exist. And the number of solutions to this equation is actually equal to the combination with repetition problem. Like in how many ways can this selection be done with repetition? Okay. So we will come to the exact solution. There are 66 such ways. I will prove it to you. Let's first try to derive the formula and then we will apply on this example. Okay. So before going to the formula, these three problem statements are equivalent. So I will read this out. So these three problem statements all denote combination with repetition. So first is the number of combinations of n objects taken r at a time with repetition allowed. So in the juice example, we had three objects, three flavored juices, F1, F2, F3. There were three objects and we had to take 10 at a time because 10 friends went to the shop. So we had to take 10 at a time. So in that example, there were three objects and we have to take 10 at a time with repetition allowed. Okay, repetition was allowed. You can take any number of F1 flavored juice. So this is one type of combination repetition problem. This is equivalent to say that. So also firstly, let's see the mapping between this statement and this statement. This we have already done. So let's see the mapping between this and this. So this is let's say statement 1. This is let's say statement 2 and this is let's say statement 3. We already know that statement 1 and 3 are equivalent. Why? The number of combination of n objects. So we have n objects. Object 1, object 2, object n. And we have infinite supply of all these. We have to take r objects. So how do we do that? We assume that let's say we take x1 objects of type O1. We take x2 objects of type O2. And similarly we take xn objects of type On. So the number of solutions to this equation x1 plus x2 up to xn is equal to r will be equal to the number of ways in which we can solve this problem. We have seen this, okay? And the condition is the condition is mentioned here, the number of non-negative integral solutions of this equation. What does it mean? That all the values of x1, x2, x3 up to xn should be non-negative, which means x1, x2 up to xn should be greater than or equal to 0. All of them should be greater than or equal to 0. Right? I hope you got the mapping, right? Now there is another way to formulate the same problem, which is statement number 2. Let's see that. So the number of ways in which are identical objects. This is a slightly trickier way to formulate the same equation. The number of ways in which are identical objects can be distributed among n distinct containers. So this is different problem now. Think of it this way. Let's say you have r identical pens 1, 2, 3, n. Okay, this is first pen, second pen, third pen, and this is rth pen. You have r identical pens, okay, and you want to distribute r pens among let's say 5 students. So first student can get 6 pens, second student can get 5 pens, and so on, right? But the equation again becomes the same thing. So let's say there are 5 students. You want to distribute these r objects among 5 students, S1, S2. There are 5 different containers. There are 5 different containers, okay, but are identical objects. So you want to distribute these among this, and there is no condition mentioned, which means that some container might be empty. So it might be possible that S1 is not getting any object, right? So the equation again becomes what? Let's say S1 gets x1 objects. The same equation, okay? S1 let's say gets x1 objects, S2 gets x2 objects, S3 gets x3 objects, and S5 gets x5 objects. Okay, I should draw this. So this is the 4th student, it is getting x4 objects. So what is the condition? That the sum of all the number of objects which all of them are getting should be equal to r. Again we are getting the same equation. So the number of different solutions to this equation is equal to the number of ways in which we can do this. So now see, it becomes tricky. These two statements are very different in some sense. Here we had n different objects. and we have to take r at a time with repetition. Okay, so this might get tricky. Okay, you have to read the problem statement very carefully. That's why I always tell you, never remember the statements. Okay, whenever a question from combination and repetition comes, read the problem carefully and always map it to an equation. Logically, map it to an equation which you can solve. A mathematical equation for which the number of solutions you have to find. Okay, we still have not counted the number of solutions. We will do it in the next slide. But that's how you should do it. Any problem statement with repetition comes, map it to an equation which you can solve and then solve it. Okay. Otherwise, you'll get confused. Here you had n different objects, take an r at a time. Here you had r identical objects, and you have to place them in n distinct containers. Okay. So, but mapping both of them to equation number 3 is easy, right? So always map them to equation number 3, and then we will solve it. So now let's solve this equation. So what we want to do? We want to find the number of possible solutions to this equation. x1 plus x2 plus xn is equal to r. We just have to find the number of solutions to this equation, where x1, x2 up to xn are all non-negative integers, which means they are all greater than or equal to 0. They can take all values from 0 to n. Okay. So how will we do that? So we shall derive this using an example. Okay, let's try to find out this example. 10 friends go to a shop and there were 3 flavors of juices. So here the equation was x1, first friend was taking okay. So for flavor 1 there were x1 juices, for flavor 2 there were x2 juices, and for flavor 3 there were x3 juices, and we have to distribute it to 10 people. Okay, so we have to find the number of solutions to this equation. So how will we do that? And I already told you one such solution is 10, 0, 0. One such solution is 0, 10, 0. One such solution is 9, 1, 0. And so on. And one solution was 5, 2, 3. So there are many solutions, okay? There are 66 solutions. How do I derive that? So there is a standard way to solve this problem. Every combination with repetition problem will be mapped to an equation, and every equation will be mapped to that logic. So what is the logic? See, you have 3 unknowns in the equation, and their sum has to be equal to some value r. So draw 12 boxes. Why am I drawing 12 boxes? You will know soon, okay? So I have drawn 12 boxes. Now, what is 12? Here 12. So see, the equation was x1 plus x2 up to xn is equal to r. So you have to draw exactly n plus r minus 1 boxes. And I will tell you why, okay? Like there is a logic behind everything. So I draw 12 boxes and I insert 2 sticks in any of these 12 boxes. You have to insert 2 sticks in any of the 12 boxes and you'll get a different solution to this equation. See how? Let's say I insert it here and here. If I insert 2 sticks here and here, this is a different solution to this equation. How? This is a solution like 3 plus 4 plus 3. You have 3 boxes here, 4 here and 3 here. You are sticking 2 sticks in these 12 boxes, right? So you will always have 10 boxes left, and they will represent a unique solution every time to this equation. So 3 plus 4 plus 3 is a different solution. For example, let's say you insert 2 sticks here and here. So what is the solution here? You have 0 boxes here, 0 boxes here, and 10 boxes here. So this is a different solution. 0 plus 10. Similarly, you can insert here and here. This now becomes a different solution. How? This becomes 10 plus 0 plus 0. This is a different solution, right? So every time you insert 2 sticks, in these 12 boxes, you get a unique solution to this equation. I hope you agree. Try and find out. Okay, you insert 2 sticks anywhere, you will have a different combination. x1 number of boxes here, x2 number of boxes here, and xn number of boxes here. So, and like we already know how to do that. We already know how to count the number of ways in which we can pick 2 boxes after 12 boxes and insert the sticks, right? Like so, it is 12C2. We just have to select 2 boxes after 12 boxes. So there are 12 C2 ways in which we can select two boxes, and we will automatically have a partition 1, 2, 3. The number of boxes will be a solution to this equation. So there are 12 C2 solutions to this equation, the number of solutions. The different variations in which we can write values of x1, x2 and x3 says that x1 plus x2 plus x3 is equal to 10. 12 C2 is what? 66. Okay? So this is how you solve this question. Now let's solve the generic equation, okay? Now let's solve the generic equation. So in a similar way, we will solve the generic equation as well. You have to solve this equation. You have to count the number of ways in like the number of possible solutions for this equation where x1, x2, xn are all non-negative. They can be 0 or any value like greater than or equal to 0. So here similar way, create n plus r minus 1 boxes. Why n plus r minus 1? I already told you in the last example. When you had n equal to 3, and r equal to 10, you actually created 12 boxes and inserted 2 sticks so that you get 3 partitions. See, this is the number of partitions that you want. Right? So you will always insert n minus 1 sticks. If you insert n minus 1 sticks, you will get n partitions. Right? So when you had like 12 boxes, let's say you have 5 boxes. If you insert 1 stick, you get 2 partitions. So if you want n partitions, you need n minus 1 sticks. So this is the number of sticks that we will insert n minus 1. And after inserting n minus 1 sticks, what do I want? I want total sum of boxes to be equal to r. Right? The total sum of boxes should be equal to r after inserting n minus 1 sticks. So the total number of boxes we need initially should be n minus 1 plus r. Right? That's how it comes. We need n plus r minus 1 boxes. In n plus r minus 1 boxes, and we need n minus 1 sticks. Insert n minus 1 sticks anywhere. So mathematically, you will have r boxes left. When you eliminate n minus 1 boxes out of these boxes, you will get r boxes left. Automatically, it will be a, so the total number of boxes left will be r. So total sum of all the elements will be equal to r. So you will have n separations and the total sum of separations will be equal to r. So that will be a number of ways in which you can actually find the values of x1, x2 up to xn such that they satisfy this equation. So how many ways you can do it? You have n plus r minus 1 boxes, and you have to choose any n minus 1 out of them. So n plus r minus 1, choose n minus 1. This is the number of ways in which we can actually select r objects out of n objects with repetition allowed. This is also the number of ways in which we can distribute r identical objects among n distinct containers, and this is also the number of ways, the number of solutions to this equation. Okay, where all x1, x2 up to xn are non-negative. So, and you can, so like see, the formula which we came up with was, n plus r minus 1 cn minus 1, and we know that ncr is equal to ncn minus r. This is combination, this is k selection is equal to k rejections, right? So this will also become equal to n plus r minus 1 cr. Okay, these and these two are equal. So yeah, this is the formula that we have. The number of combinations of n objects taken r at a time with repetition is n plus r minus 1 cr, or n plus r minus 1 factorial upon r factorial n minus 1 factorial, where n is the number of things to choose from and we choose r of them with repetition allowed, and order doesn't matter. Okay, like order doesn't matter, it is combination, just selection, not arrangement. And interestingly, you can use k rejection equal to k selection. So this formula is same as this formula. You will see sometimes n plus r minus 1 choose r, sometimes you will see n plus r minus 1 choose n minus 1. Okay, so like any of these two formulas, and they are both equal to this. So with examples it will be more clear. Okay, never remember the formula. I never remember formulas while doing counting. Okay, Always try to map a question to the equation, and solving the equation is very easy, like draw boxes and sticks. It will be very simple. So let's say this question. In how many ways can 50 be represented as a sum of, in how many ways can 50 be represented as a sum of 3 whole numbers? Whole number is what? Again the same thing, right? Non-negative integers. Whole number is 0, 1, 2 up to anything. So again, like this is a question, map it to an equation. In how many ways can 50 be represented as a sum of 3 whole numbers? Let's say that these 3 whole numbers are x, y and z. So we want x plus y plus z is equal to 50. So in how many ways can we represent 50 as a sum of 3 whole numbers? So it is equal to the number of ways, number of solutions to this equation in which x, y, z are all greater than equal to 0. Okay, the stick method works only if they can be greater than equal to 0, because that's how we did it. Like, so when we had 12 boxes and we inserted sticks here and here, so here the number of boxes left was 0, here also it was 0, and here it was n, r, right, or 12, or 10 boxes left, right? So 0 plus 0 plus 10 was also a solution. So the elements can be 0 also. So this method only works if x, y, z can be greater than equal to 0. So here how will we do it? So here n is equal to 3, r is equal to 50. So always, like, never remember the formula. If you want to do 3 partitions, you will need 2 sticks. So just add the number of sticks to this number. So you will need 52 boxes here. In 52 boxes, you just insert 2 sticks anywhere. So you will be remaining with 50 boxes, and there will be 3 partitions. So always, like, go with this. You need 3 partitions, so 2 plus 50, 52. So from 52 boxes, you need to choose 2 boxes where you will insert sticks. So this is the number of ways in which 50 can be represented as sum of 3 whole numbers. If you calculate this, it will come out to be 52 into 51 upon 2, and you can solve it, it will come out to be 1326. Okay, so this is the number of ways. Now there is a tricky question which you can try. We will discuss it in tomorrow's lecture. So in how many ways can 50 be represented as a sum of 3 natural numbers? We saw whole numbers. In whole numbers, the equation was this: x plus y plus z is equal to 50, where x, y and z all were greater than equal to 0. But now we have to represent 50 as a sum of 3 natural numbers. So the equation becomes x plus y plus z is equal to 50. But now natural numbers are numbers greater than equal to 1. So they all have to be greater than equal to 1. So you can try this out. And so this was first part of combination repetition. We will solve a few more problems in the other lecture. So yeah, we will upload it tomorrow. Okay. Cool. Thanks everyone. Bye.